This is the video for lesson number 22, Interpreting Graphs of Piecewise Linear Functions. At the end of this lesson, you will be able to interpret the meaning of each line segment in a graphing story. You will analyze a real-world situation given a graphing story. So let's take a look at the first type of graph we are going to take a look at in this unit. There are three main types. The first one is distance versus time. So what that means is our distance over here, if you take a look at the graph, is on the y-axis, and the time is on the x-axis. When we do model our real-world scenarios, the time will always be on the x-axis, the horizontal one at the bottom. So let's take some notes. A graph moves upward when distance from the starting point. So, as time goes on, and the graph is moving upward, your distance is getting further away from your starting point. A graph moves downward when the distance from the starting point. So over here, as time is going on and distance is going down, or the line is going down, that means your distance is getting less, which means your distance from the starting point is getting closer. And then a horizontal line. So in this example, the horizontal line here, as time is going on, what's happening to the distance? So let's say our distance was at 30 miles. As time is going on here, the distance is staying at 30 miles, which would mean that the distance is staying the same. This year we're going to use the word constant. Okay? So this might mean if you're driving a car that the car stopped, or wherever you are, you're no longer moving away from your original starting point. And then the steeper the line. So notice over here in the beginning of our graph, the line is slightly steeper. Oops. It's slightly steeper over here than I'd say it is over here. So some of you may know this from science class. The steeper the line in a distance versus time graph means that the steeper the line, the faster the speed. The speed is faster. So please pause if you need to copy this down. And I just want to show you this example down below. So let's model a distance versus time graph. So let's pretend this car is at their house here. So the distance from the starting point is 0. So that is why this graph would start right here. At time 0, the distance is 0. As the car begins to travel, its distance is increasing from its house. It's getting further away, which is why we have this line increasing here. So the distance continues to increase. Now, once the car has reached its location, in this example, the diner, as time is going on, is the distance from the house changing? Nope. So the distance is staying constant in our example, let's say 30 miles, away from the house. Then, once this person leaves the diner, they are going to start to head back to home, and the distance is getting closer and closer to their starting point, which represents this last line segment over here. Okay, so this one is a distance versus time graph. Let's take a look at the second one. Elevation, also known as height, versus time graphs. In this example, if you just go back to number 1, I also just want you to add here that where this arrow is pointing to, that the distance is staying constant. So constant distance is what is meant by this horizontal line here. Okay? So elevation, height versus time. A graph moves upward when the height. So as time is going on, again, time is on the x-axis, the height is getting higher and higher, so the height is increasing. The opposite of that, as a graph moves downward, so over here, it's heading down as time goes on, just means that the height is decreasing. In this example, we have another horizontal line, so the graph looks very similar to the one before. So as time is going on, what's happening to the height? It is staying the same, also known as the height is staying constant. So let's also mark that on our graph where the arrow is pointing to the horizontal line. The last part, the steeper the line. So I would say these two line segments here look pretty similar, but if one of the lines were steeper than the other, whether it was going up or going down, that would mean the faster the height changes. So the elevation is changing quicker, at a quicker pace or a quicker speed. Let's take a look at this example below. Let's say this man wants to go and climb up into this beautiful tree in his, the beautiful tree house inside of this tree. So the man goes up to the ladder. So he's at the bottom of the ladder, so our starting point is here. At time 0, his height, in this example above the ground, is 0 feet above the ground. So as he climbs up the ladder, and as time goes on, what's happening to his height? It is increasing. So that would represent this line here. So that would be this piece here. Now, once he's up hanging out inside of his treehouse, is his height changing? No. So as time goes on now, time is going on, his height is staying the same, his height is staying constant. When he's ready, he will come back down the ladder, so his height is decreasing as time is going on, and that is what is represented by the last line segment over here. The last one over here. Okay? So it looks like he climbed up originally at the same speed he climbed down, since neither of these two lines look steeper or less steep than the other. Let's check out the last graph. So another graph that we are going to see this year is a speed versus time graph. Right now, if you could please make this change right here on the second little node here, it says upward again, so please cross it out and write downward. So let's take a look at this graph. Again, time is on the x-axis always, and our other variable here is speed, which is on the y-axis. I think you get the idea now. So in this example, a graph moves upward when the speed, what do you think? Increases, or when the speed is increasing. So the opposite of that, a graph moves downward when the speed is decreasing, or whenever the object that is moving, for example a car, when the speed is getting slower. Okay? So, a horizontal line just like we did before. Let's take a look at this horizontal line here. As time is going on, what's happening to the speed? Now in this example, let's say the speed was at 30 miles per hour. So look again, if time is going on, what's happening to the speed? The car is definitely moving because the speed is still remaining at 30 miles per hour. So we would say, similar to before, that the speed stayed the same or the speed is constant. And let's label this line here. Make sure you label constant speed to the second horizontal line here. We'll get to this one in just a moment. The last part, the steeper the line. Now this one's a little tricky when we talk about speed. If one line was steeper than the other. So for example, if we had this, and then the car stayed at the same speed, and then the speed decreased. What do you think it means by this line segment in green here, where it is steeper than this one? Okay, in this example, if you guessed the faster the acceleration or the quicker the speed increases or decreases, then you are correct. The last part of this graph that I'd like to show you is this horizontal line down here. This does not mean that the graph stopped. There's just a line over the x-axis that we cannot see right now. So I want you to think about what this horizontal line means, which is going to mean something different than it did up here. So So as time is going on, do you know what the speed is here on the x-axis? If we were to go all the way over here, the speed would be 0. So at this location, this means that the car stopped, or whatever the object was that was moving. Notice that this is different from the distance versus time graph up in number 1. The car had stopped. When it got to the diner, it was this horizontal line right here. Okay, so in this example, the horizontal line on the x-axis for speed simply means that it stopped because its speed is now 0. Okay? So if I had to model this graph that was here, let's say that this car is traveling down the road at about, sorry about that. So let's say this car is traveling at about 40 miles per hour, which would be right about here. If this car is traveling at 40 miles per hour to begin with, okay, so he's moving along. Now, since the line is going down, his speed is going to get slower and slower for a little bit of time. Then when he gets to, so this one was his speed getting slower where the line is going down. Then when he gets to this orange line segment down here, the car is now stopped for a little bit. Now the line goes back up. So it kind of looks like it has the same steepness a little bit as the first one. So let's say he starts traveling again, okay? But now this time he only gets to a speed of 30 miles per hour, which would be right here. Okay? Now he's going to travel at 30 miles per hour where that blue line segment is. And then his speed is going to slowly decrease, which is represented by the last line segment over here. Okay, so these are the 3 types of graphs that we are going to observe in class tomorrow. Please turn to the back of your worksheet, and I'd like you to analyze this graph here. So let's just take some notes. Notice a couple things here. This is a distance versus time graph, so you'll want to reference the first one on the front of your page if you have any questions in mind. And in this graph, there are many line segments. I see 1, 2, 3, 4, 5, 6. So each piece tells us something different. And here's the story. At 11 o'clock, Lizzie's mother sends her to the corner store for milk and tells her to be back in 30 minutes. Examine the graph to the right. So I'd like you to try this one on your own. You're going to answer each of these questions. Really focus on the graph. Look at the numbers that are on your y-axis and x-axis. So I'm going to ask that you pause the video at this time and try this on your own. When you press play, we will go over the answers. Question A. How long was the entire trip? So all of our stories are always going to start here. So the entire trip, here's the time, okay? She was traveling to the store. When she got back home, that would be right here, okay? Because her distance from home would go back to 0. So it took Lizzie, or the entire trip was 40 minutes. Question B. What time did Lizzie arrive home? Remember from our story up above, it said that she went at 11 o'clock. So if it took her 40 minutes, she arrived home at 11:40. We do not know if it's AM or PM. Let's hope it's AM though. Why was her mother upset? Well, it said that her mom told her to be back in 30 minutes. So Lizzie was not home in 30 minutes. That is why her mom was upset, because it took her a little bit longer than she expected. Question C. How far away from home was Lizzie after 12 minutes? So that means that you should go to the 12-minute mark on your graph and go up to where the graph hits at that point. Go across to your distance, and she was 400, looks like meters away. Question D. How do we know when Lizzie arrives at the store? Well, remember from the front of your worksheet that the distance is going to stay the same once she arrives somewhere. So that's a horizontal line. So this must mean that Lizzie arrived at the store here because it's the only time that her distance from home stopped changing. So how do we know when Lizzie arrives at the store? When her distance from home will stay constant, or the same, or when you see a horizontal line. So when did she arrive at the store? Well, that's here. This would be when she got to the store. And I can see that at 16 minutes. So when did she arrive? Remember, she left at 11 o'clock, so she arrived at 11:16. Question E. How long was Lizzie at the store for? Well, we've already established that this blue line here means that this was when Lizzie was at the store. So she got there at 11:16. Looks like she left at 11:20 because her distance starts changing. So we can say that she was there for 4 minutes. F. How far away is the store from Lizzie's home? So back to what we said before. If she's at the store here, look across, and the store is 600 meters from home. Question G. Was Lizzie's trip longer going to the store or coming back? Remember that we said before up here that she arrived at the store at 11:16. So going there, it took her 16 minutes. Let's see how long it took her coming back from the store. So she left the store at 11:20. She got home at 20 minutes later. So that means coming back from the store, it took her 20 minutes. So which one took her longer? Coming back from the store. Okay. Last question, letter H. Why is line segment FG steeper than EF? So FG over here is definitely steeper than EF. Imagine you're skiing down either FG or EF. You would be going a lot faster down FG because it is steeper. Go back to the front of your page if you're not sure which one it is. And if you had that FG is steeper than EF because Lizzie was traveling at a faster speed, then you are correct. So Lizzie was moving faster. I think she was walking here, so Lizzie was walking at a faster pace or at a faster speed. Good job. Please come in with any questions tomorrow if you have, and we will continue interpreting our graphs and analyzing them. Thank you.